Okay. If you don't want to be recorded, feel free to turn your video off or watch a recording later. We'll make sure your club organizers get the link and they can send it to everyone later. So anyway, one of the first things.
Oh, real quick. If you have any questions and you don't want your voice to be on the recording, you can drop your questions in chat, and we have like 2 other people monitoring. So.
Anyway, one of the things that I always like starting to talk about is just first talking about the influence of AI. These are just metrics taken from just various statistics. For one, AI is fairly ubiquitous now. Many years ago, phones were not that ubiquitous, but now just about everyone has a phone. In the near future, just about everyone's going to have an AI in their phone at some point. If you look at your iPhone, for example, or your Android, they all have some kind of face recognition technology to recognize your face, right? That's just pure AI. But yeah, lots of mobile users are already using AI-powered voice assistants like Siri, Alexa. Netflix itself saves $1 billion apparently by using machine learning. And people even prefer using chatbots compared to humans when communicating with business. Anyway, these are just some interesting stats. So what is AI exactly? So AI is a very, 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 very broad term. AI is not just neural networks or deep learning as these common buzzwords come and go. Like these are really common buzzwords that you always hear about, but that's not the only thing. AI has been around since the dawn of computers, basically, because computers represent an AI, right? An AI doesn't necessarily need to be learning something to be called an AI. AI is anything that takes some kind of input, has some certain behavior, and gives you some output. That's literally just a computer. But some of the most popular parts of AI is machine learning, which is what you hear about all day now. Machine learning in itself is specifically a subcategory of artificial intelligence, but intersects with a lot of different domains. For example, vision refers to computer vision. Yeah, so it's a good question. What is vision? Vision refers to computer vision. So computer vision is basically a study and domain of just analyzing 2D, 3D, or 4D images, so like 3D plus time or something, making a video, analyzing these video content, image content to gain insights. Yeah, so image analysis. So one of the most common image analyses people make is object recognition. Given the meme on the left, recognize the characters in the meme, right? That's like one question you can ask. Or given this Zoom video, try to recognize who's in the video. Is it a human? Is it a boy? Is it a girl? Is it Alvin? Is it Aiden? Something like that. And then we have other fields as well. There's robotics, NLP, autonomous vehicles. So NLP stands for natural language processing. It's a field focusing on what? NLP is a field focusing on natural language processing. So this is like sentiment analysis, which refers to analyzing your text, analyzing this is like a positive feel, negative feel, what kind of emotions does it evoke. NLP also covers a lot of other things with just analyzing text. If you guys heard of GPT-3, released by OpenAI, one of the larger AI research companies, it is one of the largest language models out there. And what it does is capable of generating text like a human. We will show you some like demos of some of the things it can do, but one of the things it can do is create a completely 100% original dungeon creator or story creator. It will literally just generate stories for you. But anyway, yeah. Here's some history. Oh, who's clicking?
Sorry.
Go back.
I was gonna go ahead to that. Yeah. Okay.
Some history. There's a lot going on. So one of the first kinds of like recognized AIs is called Eliza. Eliza was a simple chatbot. It would ask you questions, you can respond to it, and it'll try to give you an appropriate response. I don't quite recall who made Eliza, but this was basically the very start of NLP work. And from there, a lot of work just spawned off. Alan Turing, you guys might have heard of. There's that Turing Award that's pretty popular. He is one of the founders of just the field of computer science and computing. Many of his main fundamentals has contributed a lot to AI. And in particular, if you don't know, the people who invented deep learning or made it popular, at least won the Turing Award, I think 2 years back. And just some other things, and we move to modern day. These are probably some of the biggest companies doing AI. So you have Facebook, Google, DeepMind, Amazon, OpenAI. The top right one is actually not a company, that's a framework. And DeepMind in particular is actually owned by Google. But basically, there's a lot of big companies that are doing AI. Next slide. So these are just some common terms in this field. There's a lot: reinforcement learning, deep learning, AI, sigmoid, bot, hyperparameters, machine learning. A lot of things are very, very confusing sounding. Like if you didn't read a book on this, or spend hours and hours through lectures or something, you probably wouldn't know many of these. But that's why we have this workshop, to try to clarify some of these. I think one of the most important things when you want to get into AI is just first understanding the jargon or just some of the literature. So next slide. So yeah, I'll explain a little bit more about what AI is really all about. So it's not all just about neural networks. There's a ton of mathematical tools for machine learning. So prior to deep learning, a lot of object recognition, image analysis was performed using what's called classical algorithms, classical computer vision algorithms. A lot of problems, like let's say regression problems, you guys might have learned in high school, which is like given a set of points, how do you find a line of best fit or curve of best fit? Those are all solved with traditional analytical solutions. So basically explicit solutions that automatically give you the line of best fit. But these days, AI is able to automate all of that and do all of that with just neural networks and deep learning. But at its very core, neural networks are actually just a lot of stats and math. This is just a very non-exhaustive list of various algorithms or models that are used right now. They're still very popular. So SVMs, support vector machines, linear polynomial logistic regression, different degrees of programming, PCA, Monte Carlo tree search, which was used by DeepMind to beat the world's best AlphaGo player, gradient descent, genetic algorithm, literally an if statement. Next slide. But AI is not all just about like the stats and algorithms and models. It's also about systems, computation, and also more math. A lot of computing goes into doing all these predictions analyses, and it's not possible to do that much computation without good hardware and good system design. So one of the some of these fields include robust AI systems, cloud AI for making AI more accessible. So like small businesses and other businesses around the world can leverage the power of AI. GPUs, TPUs, hardware acceleration. These are just various hardware components that allow you to compute matrices, operations, and compute various operations in a parallelized format, which speeds up time a lot. Parallel computing, quantum computing is actually very new. People in the research field of AI are actually looking into quantum ML and its possibilities. There's auto ML, which is automatic machine learning, which Google has coined nicely. And some more math terms like auto differentiation and computational graphs and much more. You don't need to worry about exact specifics, but these are just some things to keep in mind. Next slide. So here are just some cool demos. We can show like one of them or a couple of them. So yeah, we can just show the first one.
Okay.
Yeah. So this is something you can do with neural networks. If you haven't heard of, there's something called a style transfer neural network, which is what it does is takes an image, an art image, and combines them together. So try clicking an image, for example. So this will take a cat, it'll download a model, compile it, and then run it through, and it'll give you a stylized image.
Whoa.
So if you can guess, this is The Great Wave by that Japanese artist. I cannot remember his name. And that cat image put together. And you can do this with a load of different images. But yeah, this is basically done with just a neural network. Another example is hide and seek. So this is a really cool video. Yes, computer vision was used in the last one just now. But this is a really cool video. So this was run by OpenAI. So they had two agents playing hide and seek, hiders and seekers. In the game, there are boxes and like ramps where they can run up, block locations. And you'll see that these agents use reinforcement learning to learn and to stop themselves from getting seen by the seekers. And eventually you see that they learn very interesting strategies. Actually, at one point, they actually cheat the game. The RL models somehow, the agents, the hiders somehow learned to cheat the game. I think they went off the map somehow. I don't quite remember. But yeah. Yeah, this is kind of like game AI. Specifically, the field of RL does a lot of work in games. they typically like to use a lot of games to develop an AI based off of it. So here's the thing using OpenAI's GPT-3. This is using the largest language model. This language model is basically generating an AI dungeon. It will generate a story. So you can see here, this one's talking about a spaceship. If you tell it something you want to do, it'll react pretty appropriately. So you see Aiden play around with the AI dungeon.
Yeah, they trained this on a bunch of like choose your own adventure stories.
So you see that the AI automatically recognizes that you're trying to investigate a signal and then generates new stories about that signal.
Yeah, really cool.
Yeah, talk to transformer. So transformer is probably referring to what's called a transformer module or network. This is very often used in NLP. Yep, it's very often used in NLP, and it's used to help generate text. It's like generating an essay. Although not that well, but there's a lot of things you can do. And he do like really silly things in this. Like if you tell your guy to just jump into space and suicide, it will literally do it. Anyway, next example. I think I have the Minecraft one up.
Oh yeah.
Yeah, show the Minecraft one.
Yes. This was created by Aiden. He basically used Minecraft to create a neural network. And we'll explain how neural networks work a little bit more in depth, but here's just a quick, cool video.
I don't know if you guys can hear it. I don't think you can hear it.
Yeah, I don't think the sound's coming up, but you can try.
Oh, okay. I'll skip to it's basically just implemented. So you can like hook everything up using like leads and fence posts and stuff. And then yeah. It's pretty cool. You can find this on YouTube if you want to watch it.
We left the link in our slides, which also we should share. Does someone have the slides?
I can link the slides.
Send the slides into Zoom.
Also, Aiden has 12.9K subscribers on YouTube. So
Yes. This man's
on his way to 13K.
Yeah.
Do we have link sharing enabled?
Make sure anyone can view it.
Copy link. Okay.
You have to click the change link to ACM.
Oh, okay.
And then do anyone.
Oh, with link. Awesome. Okay, I'm putting it in chat. There we go. Okay, back to the presentation.
Okay, yeah. So we kind of talked about some of the demos of neural networks and everything. But what about now we're going to talk a little bit about some of the math behind it. So one thing, maybe this will be review, maybe this will be new, but one mathematical concept we want to talk about first is matrices. So just a simple introduction to matrices. It's pretty much a rectangular array of variables or constants in a horizontal row and vertical columns enclosed in brackets. So you can see a couple examples on the side. For example, the first matrix A, has 3 by 2 dimensions. There are 3 rows and 2 columns. And second one, 4 by 1. Third one, 2 by 4. And each value in this matrix C could be a number. It could be a letter or a constant, is called an element. And as I mentioned, we take the number of rows and the number of columns as the dimensions of a matrix C. Next slide. And so here are some examples of matrices in action. So I showed the dimensions thing, but for example, if you have on the image on the right, you have 2 matrices and you set them equal to each other, you can actually use algebra to solve like what are the constants you have in this matrix C. So for example, you have 2x plus 3y equals y and 12, right? So you can set the top 2 elements equal to each other, 2x equals y, and then 2x plus 3y equals 12, and then you can use simple algebra to solve what x is. So, hopefully that math part is a little bit review, but if not, you can review some algebra on the side. Next slide. And, this is just a little bit more complicated version where you can, again, you're setting the equations equal to each other and you can check your answer. That's an example. There's another example on the right side, set each element equal and solve. This is a little bit weirder because now, it's longer than it is wide. It is longer than it is tall, yeah. So now you have what, 2x equals 5, 3 equals 3y, 3z equals 9, and then you can solve that again with algebra. And we'll maybe it might be kind of unclear how matrices will be involved in neural networks, right? But this will hopefully be more clear later on, a little bit later on in this slide, in these slides. Next slide. So the purpose of a neural network is kind of to simulate what actually goes on in your brain, right? So your brain is made up of a bunch of neurons, and similarly, neural networks are made up of a bunch of neurons too. So we here have like a definition of a neuron, or also called a perceptron. They're the basic building blocks of a neural network, also basic building of your brains, right? And one important thing about one important difference between neurons in your brain versus neurons in a neural network is that neurons in your brain, they fire at the same amplitude but different frequencies. But neurons in a neural network fire at different amplitudes and the same frequency. And maybe this will make a little more sense later on. But that's just an image of a neuron. This is not a good representation of a neuron in a neural network, but this is more of a neuron in your brain. Next slide. So we kind of okay, what do amplitudes and frequencies? So maybe it'll make a little bit more sense later. Aiden will talk a little bit about what happens when you put a bunch of neurons together, right? Or in your neural network, you'll have multiple layers, and it's important. Maybe it'll make a little more sense what amplitude and frequency mean when you see like all the neurons put together in terms of layers. But
real quick, the main difference is biological neurons are all or one. It's either a 1 or a 0, but in neural networks, it can be variable. It can be -1, 0.5. It can take on a range of values. And so in our brains, the way we convey amplitude is through like flashing, like doing a bunch of ones really fast. Yeah, sorry.
Oh no, yeah, thank you. Thanks, Aiden. Yeah, so yeah, what Aiden said. And Stone also has a great description in chat too. But now we're going to talk about, what exactly does a neuron in a neural network do? So this is on the left, you can see a diagram of a single neuron in a neural network. And what it basically does, it takes in a bunch of inputs, and based on these inputs, it evaluates a certain sum, right? And then this neuron also has an aspect called a bias, where it adds this bias, and then this result is fed through an activation function, which could be bias, or yeah, can someone answer chat? And this function, it could be linear, it could be nonlinear. There are a lot of different functions for activation functions. And so sometimes, how we make jokes about, oh, my last brain cell during a test, or something like that. That's kind of like your one neuron making, like a single neuron making just one tiny decision. Like it just makes one tiny decision. And so when you put a lot of these together, it becomes a lot more useful. So in the next slides, Aiden will talk a little bit more what happens when you put a lot of these neurons together, and yeah.
All right, so the next step, now we understand how one neuron works, but what's like really important is to understand how these neurons can come together to form networks of neurons. So the way a neural network, like a basic neural network works, is you have input neurons and you feed your inputs into this input layer. And then the values in the input layer, say this first one was a 1, they get multiplied by the weights and passed on to the next layer. And then everything in the next layer gets added up and it gets passed on. And each neuron will add its bias to it. Yeah, so you can think of the weights as the strength of the connection between the two neurons. So if the one pathway, you can look through the network and see that, oh, this one pathway is really important, or this neuron makes, if this neuron fires, it makes another neuron less likely to fire. And what's important to visualize is, like, try to convince yourself that if we had a big enough network with enough neurons and we just magically knew what to set all the weights and biases to, that we could solve all sorts of problems, like image recognition, or like recognizing if there's a 6 if we passed in all the information about an image. Yeah. Okay. So yeah, this is what I was talking about. Like, convince yourself that it is possible, given this architecture, if we made it big enough, that we could do almost anything. Now, what's really important is how, like in practice, how do we actually figure out what to set all the weights and biases to? And a lot of the artistry of machine learning goes into figuring out how to set those weights and biases. And these are generally called learning algorithms.
Okay, yeah, so now we kind of have a idea of, what happens when you put a bunch of neurons together in a neural network. And, we introduced matrices earlier. So now how exactly do matrices tie in with neural networks, right? So matrices are actually a very efficient representation of a neural network, right? So, recall Aiden just explained how neural networks are, layers upon layers of neurons, and they connect in a directed graph. And what a directed graph means is that between nodes, aka neurons, between two neurons, directed means that it only goes in one direction, right? Rather than it can go back and forth. In a directed graph, it means it can only go in one direction. So in all these layers, you can only go in one direction in between neurons. And one common way to represent these connections is through a adjacency matrix. And I have an example of an adjacency matrix on the left. So you can kind of see in this example, one signifies yes and 0 signifies no, right? So let's just take a look at the very top of that graph. We have the letter or neuron Y connected to neuron Z, right? Or node Y connected to node Z. And if we take a look at our graph, we take a look at row Y and row Y, and you can see that row Y column Z, row Y column Z is 1, right? Which signifies that Y has a connection to Z. But if you go ahead and look at row Z, column Y, that's a 0, because row Z cannot go to Y, but Y can go to Z. And so this is a pretty common way to represent layers upon layers of neurons in a neural network. And if you think about it, there's so many different neurons in a neural network. So each one of these, these matrices will be massive, right? And so it will take a really long time, but thanks to GPUs and TPUs, matrix calculations are a lot faster than they used before. In the past, they use for loops. They take a look at every single connection, but now we have like parallel computations, things like that. Parallel computation, meaning like you kind of do these computations at the same time. They're so much faster now. So yeah, next slide.
Yeah, so now we're gonna talk a bit just about what makes neural net so powerful. The main purpose of a neural net is not, well, for one, there's actually a very important theorem about neural nets, which is saying that a neural network that's large enough can approximate any function. So in its essence, neural networks are just functions, like f of x equals x squared, or f of x equals sine of x times x minus e to the x or something. Like all neural networks are doing are just modeling an arbitrary function. So what scientists are effectively doing is we're assuming that for, let's say, image recognition, there is some mapping from an image, like its RGB values at each pixel of the image, to a classification of cat, dog, or other or something. We assume there's some function like that that is continuous or is like learnable. And we want to make a neural network to approximate and to change its parameters, its weights and biases, such that it gets as close as possible to the ideal function that gives us the correct mapping. So in general, how does a neural network learn? Well, at a low level, a neural network only changes behavior when its weights and biases are changed. So naturally, we can think that a neural network learns by doing that, exactly that. But how does a neural net learn to be better? Because if you just randomly change the weights and biases, right, you're probably not going to get the intended result. Like you have no goal in mind, how you're gonna achieve the goal. So how does a neural network learn better? Well, one of the most popular ways, and probably the only way that most people use, is we establish some goal using a mathematical function. Typically, this function is called the loss function and represents how far off our neural network's predictions are from the real data. So as an example, let's just say our loss function looks like the thing on the left. A loss function takes in parameters in our network as input and outputs, sorry, let me repeat that. A loss function takes in parameters and takes in the input data and outputs the loss of that, the loss. So for example, if our input data is an image of a cat and we have some random parameters initialized, this loss function will tell us passing how far away our prediction of it being a cat our neural network is. So for example, if we pass the image of the cat using their current parameters, if we have a high loss, that means we made a poor prediction. Maybe we predicted that it was actually a dog when it is actually a cat. But if our loss is very small, then it's more likely that our neural network predicted the accurate thing of that it is being a cat. And we'll talk about this a little bit later, but typically with loss functions, the way we use it to help the neural networks learn for the best is to find the parameters such that the loss value is as small as possible. So if you look at the graph on the left, you guys probably learned about minimum values, right? When we have a function, sometimes it's going to be a minimum point and you want to find that minimum point. All right, next slide. Okay. I'll just cover this one as well. So yeah, so as I repeated said, loss function is typically a function that takes in a neural network model, its parameters, and also takes in a sample set of data points and outputs a loss, representing how poorly our network is able to predict on the data points. And for example, as an example, data points can be generated by some known functions such as x squared. It could also be image data. And we want to minimize the loss function by changing the weights and biases. There are many popular minimization methods, and this goes into an entire separate field from AI that is now being connected to AI a lot because of this problem, which is called numerical optimization. One of the most popular methods for numerical optimization that you might have heard of is gradient descent. There are many, many others, especially for some problems where convex optimization is easily done. There's many other, even more algorithms. But yeah, we'll talk about some of them. We'll talk about gradient descent and also talk about some naive and simple ways as well. Next slide. Aiden?
Yeah. So first, we're going to go over some simple ways to minimize loss. So if our loss function was a simple quadratic function, we could actually calculate the minimum, like using math, if we only had a few parameters, like 2 parameters or 3. But as we start to scale up our network, it starts to become like impossible, almost impossible to mathematically calculate the minimum of the cost function or the loss function. Another simple way is to manually tweak the network's parameters until it gets lower, which you can also do. You can move them and experiment and tweak with it by hand, but as the network gets bigger, it's virtually impossible. Another way that you can do this is taking a genetic approach. You can randomize, like have 1,000 different randomized versions of the network and see which ones are the best, and then take a couple of those and then make small steps. Like you have this one network that's pretty good, and then you can randomize all the weights plus or minus 0.01, and then you have a whole another generation. You take the best in that generation and you keep doing it over and over and over. And eventually your network is going to get better. That's just like how evolution works. But all these methods work, but they are not really efficient, especially as you start to get bigger and bigger networks. So we're going to talk about some more efficient methods next. So now we're going to talk about gradient descent in general. So I don't know if you guys are familiar with derivatives and gradients, but they measure the change of a function with respect to one variable. It itself is also a function. So speed, for example, is distance over time. And in physics, it's actually the derivative of displacement with respect to time. We're going to visualize this more, but basically what's really important is what a partial derivative is just we have this big function and we want to just change one variable, like one weight, and then see how that affects the overall output. That's the big picture here. Stone, you want to take this?
Yeah. Someone just mentioned a great comment. We're basically trying to find when the derivative is near 0 to find the minimum, and you will actually see this. So let's suppose that we have a red curve. This function is actually just a parabola. I think it's like x minus 0.5 squared or something. And you'll notice at each point I've drawn arrows. So these represent the derivatives. The derivative just represents the change in the function at that point. So the way you draw these derivatives, basically you just take a tangent line, draw through that point, that's tangent to that point, and you can find that arrow. So you see that as we go down this parabola, that's about like an expert function, the arrows start to slope up, 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 and up, and it starts completely sloping upwards. So you'll also notice so when it's sloping down, the slope is equal to the derivative. So you notice that at the very bottom point of this convex function, this convex curve, this parabola, the slope is actually 0, which is actually, in the most simple case, is usually a local minimum or a global minimum. To be more specific, there are things called convex functions, things called concave functions. A convex function looks like this, where there exists a global minimum. A concave function does not have a global minimum. So when the derivative is actually equal to 0, there are times where it's not equal to the minimum, and there are times when it is equal to the minimum. So I'll show you this example here. You'll see that there are local minima and there are global minimum, which can be a little bit confusing. So you see that the third local minimum is like, it is a minimum in its local region, but it's not the best minimum. And you have a maximum area, such as the point up there, right to the left of that, where it's a maximum, in between the two. Yeah, so that's a maximum, which also is derivative of 0. So that begs the question, how do you find the actual minimum? There are minimum numerical methods. If you know a bit more calculus, you know that taking the second derivative allows you to determine the maximum or the minimum. Go back to the original slide, the slides. Yeah. So if you look at the second derivative, actually, you'll see that the second derivative measures a change in the slope. So you notice that throughout the whole time, the slope is always going up. So the second derivative is actually positive, which implies that here at the minimum, it is indeed a minimum. Now, someone mentioned a point about gradient descent being stuck at saddle points. Yes, that is very true. That is a much more complicated thing. Saddle points are actually refer to points in a plane, in a curve such that I'm trying to think of a better way to say this without saying something about the Hessian matrix. Okay, you can imagine a saddle point as in one direction, it's in one direction it is increasing to a maximum, in another direction it's decreasing to a minimum at a saddle point. So if you think of the function x cubed, that's a little bit like that. It's 0. It looks a little bit like that. Not the best example, but it's an example. Yeah, anyone have any questions about just derivatives and minimums and how, like, it's a simple case you can find a minimum using derivatives? All right, next slide.
So the gradient is equal to the partial derivative of the cost function with respect to each of the weights and biases. Or in other words, the gradient is like a vector with a bunch of numbers in it, and it has a number for each individual weight and bias that represents how much the cost function would change if we only changed that one weight or bias by a super small number, like 0.00001. So you can imagine this as like a three-dimensional, or really it's like a super high dimensional, but you can picture it in just a three-dimensional space where it's like a ball rolling down the hill. That's like what we want to do. So once we have the gradient tells us which direction to go in order to increase the cost function or the loss function the fastest. So if we want to decrease our loss, we want our loss to go towards 0, we can take a tiny step in the opposite direction of the gradient. And if we do that over and over and over and keep recalculating the gradient and then taking a small step, we will like go find a local minimum. Yeah.
Also want to mention, someone else was talking about learning rates. So this is actually where learning rates get applied. So you'll notice that in the bolded text, we say that we changed one variable by a small number, like 1 to the power of like 10 to the negative 6. The amount we change by, we scale that using a learning rate. So if we have a high learning rate, we'll change our variable by much more. Or sorry, we'll change our parameters by much more. If you have a small learning rate, we'll change our parameters by much less. So what you can imagine is that if our learning rate is super large, we're actually going to jump across this map, this loss curve that we show in the graph, a lot. And typically when you have too large of a learning rate, you could actually jump over the minimum and never find it. But if you have too small of a learning rate, you can also see that it'll take us forever to get to that small part. So you see how in the graph there's like these different stars or these crosses. Those measure our iteration, like where are we in the loss curve at each iteration. If the learning rate was really small, we would have like millions of those little crosses before we ever hit the minimum. But if it was, so if it was a larger learning rate, we would have much less crosses, but we would probably be jumping around a lot, not finding the minimum appropriately. And this gives you, this is actually a very active area of research, just basically how to minimize the fastest. There are many, many algorithms. There's things called ATOM, AutoGrad, RMSProp. There are other numerical methods, such as decaying the learning rate over time. So like you start off with a large learning rate, and then you learn slower and slower and slower to make it more accurate. There are other things called cyclical learning rates, where you start from a high learning rate, go down to a small learning rate, then go back up to a high learning rate, and then go back to small. There's basically a lot of creative things you can do. Yeah, but yeah, that is most of it for today's workshop. These are just some of the resources. So there's something called a neural network playground, which I'd like to show you guys. This shows you a very simple neural network. So you see right now it has 2 inputs, x1, x2, and has a middle layer of 4 neurons and a final layer of 2 neurons. And the data we have is like a circular data. So what you will notice is that this neural network can learn to predict the decision boundary. So that white line is what's known as decision boundary, which tells us when to predict one class versus the other. And here our 2 classes are just blue and orange. And yeah, so you can play around with this network. It gives you a nice tutorial of how to use this. So you can add more layers, you can add more neurons to see how it affects the impact of your neural network. And you can also play with other activation functions, which we didn't go too deep in, but basically recall that when we're having a neuron, we take the sum of the weighted inputs plus the biases. What also happens is that we pass that through a function to transform that one additional step. For example, ReLU is a simple function. What it does is it takes that weighted input and outputs 0 if it's too small, outputs the same value if it's greater than some threshold, I think. And there are many other ones. Yeah. Yes, Alvin provided a good link.
Plug.
All right. Do you guys want to add any other comments? Also, feel free to ask us as many questions as you want. We can maybe answer most of them. Who's cooler, Alvin?
And what's cool about this website is you can actually see each of these neurons is taking the inputs and like learning to draw a line at one point, and then all of these like boundaries are being combined to form a circle, like being added and subtracted. So that's like how it's doing it. It's pretty cool. And you can see all the strengths of the weights and biases. Very cool.
All right. I think I'll close the recording for now. I think that's basically it.